Hello! In this video we will talk about the heating and cooling grids and their role in integrated and intelligent energy systems. The learning objective of this video includes a short historic overview of existing heating and cooling grids and the differences between these different generations of heating and cooling grids. Then we look at the major challenges to decarbonize the heating and cooling supply, and finally we look into future research directions in this field. Heating and cooling grids have been developed since the late 19th century. Initially, these were steam grids with supply temperatures around 200 degrees Celsius. In the second generation grids, these temperatures dropped significantly and hot water was used with centralized combined heat and power plants with one directional supply to the buildings. In the third generation grids, which are typical for most of the existing large-scale heat grids at the moment, we see that multiple large-scale heat sources are being applied, such as industrial waste heat, centralized biomass boilers and CHP plants for district heating grids. Temperatures are still typically well above 70 degrees Celsius. Coming to the fourth generation grids, which were introduced around 1 or 2 decades ago, we see the introduction of more renewable sources, geothermal energy sources, and other low-grade waste heat sources. As a result, temperature further drops in these fourth generation grids. However, a big challenge is appearing when we shift to so-called fifth generation grids. This is because the temperatures are further going down and it is becoming feasible to combine both heating and cooling in the same grid. This means that the heat supply needs to be upgraded at the individual building level using heat pumps and electricity. We will focus on the differences between the existing and future grids in the next slides. In the third generation heat grids, the supply temperatures are still high, between 80 and 120 degrees Celsius. They require centralized circulation pumps for the heat distribution. Further, since the supply and return temperatures are high, the exact value of the return temperature is less relevant, as heat sources such as gas-fired boilers can produce any temperature that is required. In a fourth generation grid, there are more medium temperature sources available, hence the return temperature must be lower as well and becomes more relevant, but is still not a key performance indicator. Also, centralized circulation pumps are still required. Hence, in terms of controllability of the grid and design, the fourth generation and third generation grids are very similar. But the difference really appear when we go to fifth generation grids, because in that case individual buildings may use cooling from the grid, which means they automatically provide heating. This makes the return temperature a key performance indicator. Another significant difference is the use of circulation pumps at the individual building level. The buildings may extract from the warm and cold line as per requirement, and therefore centralized circulation pumps are not required anymore. This allows bidirectional flow of heat between these sources and between the individual buildings. So the fifth generation grid can supply both heating and cooling simultaneously and is characterized by an innovative design concept as compared with earlier generation grids. For decarbonization of the heating cooling supply via thermal grids, there are certain challenges involved. These can be broadly classified as planning and operational challenges. One of the main planning challenges is the determination of future peak loads. Integration of heating and cooling grids with the power grid using heat pumps makes determination of future peak loads challenging. Other factors, such as decisions made by humans on investments to insulate buildings and their willingness to apply peak shaving strategies, make the determination of these future peak loads complex and highly integrated and challenging task. Also, the need for coordination between buildings, the thermal grid and the sources for efficient energy utilization is also a planning challenge that needs to be considered. Other challenges include the overall decision to develop a collective heating solution anyway, or to apply individual sustainable heating solutions. Operational challenges include this optimal integration of electricity consumption for heat pumps together with heat storage at the building level or heat storage at the grid level. Other major operational challenges involve short-term demand and supply matching, limited capacity of low-temperature heat sources, and operation of bidirectional flow between sources in the future heating cooling grids. The future research directions, as already illustrated in the challenges, involves an assessment of these future peak loads for both heating, cooling, and electricity in these so-called smart energy systems. This is because of the high level of integration, which is unprecedented, and there is no historical experience for predicting these peak loads. Another research direction is to combine behavioral sciences and technical systems analysis. This is required as investment decisions by both individuals and communities on developing heating and cooling grids and the assessment of individual behavior. These all impact the future peak loads. So the combination of behavioral science and this technical systems analysis is a new field of research which is essential for intelligent and integrated energy systems. Lastly, one of the key operational challenges that requires further research is more advanced control strategies. These are required for optimal operation of thermal storage along with these power and thermal grids. In conclusion, we have talked about development of existing and future district heating and cooling grids. Then we talked about the major planning and operational challenges involved with these grids. And finally, the most important research directions in this field were quickly highlighted. That concludes this short lecture. Thank you for your time.